Good design can change the world, but so too can bad design. No more apparent is the importance of solid engineering than at sea, where the ocean, in all its infinite might, is trying around the clock to destroy the very ships that float on its surface with seemingly endlessly creative means. We've explored a lot of wrecks on this channel, but these three are some of the most interesting because of their engineering implications. Ladies and gentlemen, I'm your friend, recovering from the flu, Mike Brady from Oceanliner Designs, and while I recover, here's a look back at 3 design and engineering failures that proved to be deadly. Ocean liners are designed to get people from point A to point B as quickly as possible over very large distances, and I've often referred to them as big, luxurious ferries. But the humble ferry shouldn't be underestimated in any way, because these ships also battle through some of the harshest seas in the world, but their development and use has not been without serious incidents, and it's all down to one fundamental Achilles heel. Early ferries took people to nearby locations across water and would winch and manhandle critical cargo on board with cranes or booms. But by the 20th century, cars had taken over as the main form of transport for people over distances on land, and ferries had to be updated to keep with the times. Most passengers had their own cars, and so taking hours to winch individual passenger cars on board, one by one, just wouldn't do. A simpler, faster solution would be needed. Now this birthed the so-called roll-on, roll-off ferry, or ro-ro for short, where passengers could just drive right on up and into the ship themselves. Now you're probably familiar with this type of ship because they're very much in use today, but in the 1940s it was a revolutionary new development, and roll-on, roll-off ships were built to operate on short routes across the world. Now the ability for passengers to drive up and straight into the ship required some design quirks, to say the least. In order to actually get passenger cars on board, a fairly sizable hole would be needed for them to drive through. Now, doors had to be fitted to the ferry's loading bay to keep the ocean out and to keep the hull watertight. Early ro-ro ferries featured doors at their stern on the back of the ship, and right off the bat, having a massive hole in your ship's hull that can cause massive and unchecked flooding is an obvious red flag, and the vessel's safety will come down to the integrity and strength of the doors actually fitted to protect the hull. Now, in a normal ship, watertight compartments would be able to be sealed shut and prevent water from flooding through to the rest of the vessel, but early ro-ro ferries also needed to keep their lower decks clear and open so that cars could actually be driven in and parked. They didn't have watertight compartments on the car decks. Now, this is also a massive red flag as far as ship design goes, but so long as those doors held up, then there shouldn't have been an issue. Well, this was all put to the test, a few times actually, but the first, in January 1953, when the early ro-ro ferry Princess Victoria was battling her way through a nasty sea between Stranraer in Scotland and Larne in Northern Ireland. With a gale warning in effect, the ferry put to sea with 179 passengers and crew on board, but it was noted soon after that waves and spray were breaking over the ship's stern and hammering in the doors. Now, this should not necessarily have been a problem. The designers had fitted sliding doors as well as an additional protection in the form of a guillotine door, which would actually drop down like the name implies and provide an additional seal against the water. But there were a few issues. In the day-to-day operation of the ferry, it was found that actually using the guillotine door was impractical and slowed down the whole operation, so it was rarely, if ever, used. But more critically, if the door was damaged at all, it couldn't drop down. And it just so happened that on that January day, the guillotine door was damaged and unable to be lowered. Then massive waves began to burst through the stern doors and the crew couldn't shut them. With water pouring in and unable to drain, and with no watertight compartments to stop it, the ship began to take on a list to her side, but her captain did his best to change course and keep the stern out of the worst of the waves. With the list worsening and a rescue mission actually struggling to find the ship, it became clear that Princess Victoria did not have long to live. The lifeboat, Sir Samuel Kelly, bravely battled its way through the heaving seas and actually managed to carefully rescue as many as it could before the ferry completely sank and took 153 passengers and crew with her, leaving only 44 survivors. Now, a subsequent inquiry found that the doors had not been designed with enough strength, and they couldn't hope to stand up to the kind of heavy sea one might expect to encounter between Stranraer and Larne. To add insult to injury, though, the scuppers, which were essentially drains intended to carry out any accumulated water in the car decks and dump it over the side, were found to be totally ineffective. So obviously, Princess Victoria was a ship with a few design faults, but surely fitting a heavier duty set of doors would remedy the issue. Well, years later, in 1994, another Ro-Ro ferry very famously met disaster, all thanks to the design of its doors. The Swedish Estonian ferry Estonia was a decently sized thing, about 15,600 gross tons and around 515 or 157 meters long. She could carry 2,000 passengers and no fewer than 460 cars between Tallinn in Estonia and Stockholm, Sweden. Now, on September 27, 1994, the ferry set off for Sweden, but encountered heavy seas, up to 20 feet or 6 meters tall, and a wind speed equivalent to a force 10. She battled her way forward for hours, pitching and rolling in the massive waves, when at around 1 a.m. there was a loud bang that reverberated through the ship. A quick inspection from the crew showed no issues. Warning lamps did not sound, and all seemed well. Except the banging sounds continued, and then, just 15 minutes later, Estonia began to roll onto her starboard side. Now clearly something was terribly wrong, and the general emergency alarm was sounded, but things happened too quickly for the ferry and her passengers and crew. Just 50 minutes after the first sign of trouble, Estonia was gone, and she had taken around 850 of her human complement with her. Now, this is actually ranked as one of the worst peacetime shipping disasters in modern history, and immediately the cargo doors were an obvious suspect. Unlike the Princess Victoria, by this point, Ro-Ro ferries were being built with bow loading doors where the ship's forward end would essentially open up like a giant mouth and passengers could drive right in. It made loading and unloading even faster, but obviously those doors had to be able to withstand a huge amount of force, because at the bow of the ship, they would need to bear the brunt of all the ocean's might. It's not an engineering impossibility, but it's difficult to pull off with certainty, and it just so happens that Estonia's doors featured a design fault. The bolts which actually secured the doors to the hull had failed under the strain, and then the complex ramp structure behind it was dislodged in such a way that the alarms weren't rung, and the bridge had no idea that the door was now technically open. Forging ahead, more and more seawater was forced into the hole, and then the vehicle deck. Being the middle of the night, the deck was uninhabited at the time, no warning was sounded, and it was flooding with tons and tons of water. The result was a free surface effect, where all that unchecked water would unbalance the ship, and it resulted in Estonia rolling completely onto her side. Remarkably, Estonia's bow visor, or door, the entire forwardmost section of the ship, was recovered intact, and the inquiry established that, incredibly, the visor was not considered crucial to the ship's safety. It was the inner bow ramp's failure afterwards which had allowed the water to enter. Ro-Ro ferries are unique in that in order to actually operate, they really need this design Achilles heel, a massive loading port in the forward or rearmost part of the ship so that cars can get in. And coupled with that uncomfortable fact was the added design quirk where most other ships feature the complex watertight compartments to prevent ships from flooding if they do start taking on water, but the Ro-Ro ferries needed to have that contiguous deck free of bulkheads or obstacles so that cars could actually get in and around in the first place. All the success and safety fell down to the design and safe operation of the doors. It all comes down to how well engineered and strong those doors are in order to actually keep water out and keep the ship's hull watertight at all times. Lessons were taken away, and the concept of the Ro-Ro ferry had been refined so that they are very safe indeed. But human error can still creep in, and no matter how well designed your ship is, people can and will find a way of messing things up occasionally. So it was in 1987 that the Ro-Ro ferry Herald of Free Enterprise was departing on a routine voyage from Dover to Zeebrugge in Belgium when the ship began to take on an enormous amount of water. Within less than half an hour of departure, and with about 550 people on board, the ferry capsized in just 90 seconds. It killed 193 people, and the cause of the disaster was frustratingly simple. Those huge, safe bow loading doors were simply never shut. The crew, under pressure from constant operations and tight schedules, had failed to ensure the doors were closed, and the skipper put his ship to sea simply assuming that they had been. The inquiry called the mishandling of the ship a, quote, disease of sloppiness, and incredibly, earlier calls for alarms or indicators actually reporting the position of the doors were ignored. It's surely testament to human engineering today that thousands of ro-ro ferries operate safely around the world, and the might of the ocean is held back by the clever design of the loading doors. The 16th of January 1943. It's a calm day at the Swan Island shipyard in Portland, Oregon. The brand new SS Schenectady lies peacefully at her moorings, having made it back safely from her sea trials, and she now awaits preparations for war service. But all of a sudden, a deafening crack rings out across the shipyard, echoing as far as a mile away. Out of nowhere, and for seemingly no apparent reason, the Schenectady's hull has cleaved almost completely in half. The incredible shipbuilding effort undertaken by the Allies in World War II saw the creation of thousands of vessels. T2 tankers, Victory, and especially Liberty ships have gone down in history for a number of reasons, namely their integral contribution to the Allied victory of World War II, the incredible story of their creation en masse, but, on a rather less positive note, their early tendency to split in two. As if afflicted by some kind of curse, the Schenectady was far from the only war industry ship to meet a catastrophic end. But what added still further to the growing worry surrounding these ships' failures was the mystery of why they were breaking in half at all. With multiple ships having split apart without a clear apparent cause, something was evidently going very wrong, and would go on to teach lessons in shipbuilding that are still in use to this day. Ladies and gentlemen, I'm your friend Mike Brady from Oceanliner Designs, and this is the story of the ships that broke in half. When the US joined the war, the Battle of the Atlantic had already been long raging, and the Allied forces were struggling to hold their own in what was effectively a war of tonnage. Merchant ships were being sunk by German U-boats at a staggering rate, persistently prowling the waters in search of their targets, and British shipyards simply couldn't build enough ships fast enough to replace those that were being lost. The situation was dire. In just a few months, from the beginning of March to the end of May 1941, 142 merchant ships were lost to U-boats. Without some kind of intervention, and fast, it looked like an Allied victory would inevitably slip out of reach. Cue the help of the United States. The pressing need for replacement ships set in motion the production of Liberty ships as part of the $350 million emergency shipbuilding program. Now, before this point, the established construction methods for ships like that were, frankly put, just way too slow to meet the incredible demands of wartime. Now, unlike the previous standard for riveted construction, the significant time pressures at play here required a more time-effective alternative: welding. The man behind this new approach to quick and efficient shipbuilding, the American industrialist Henry Kaiser, created the namesake Kaiser shipyards, which would go on to significantly outperform all other shipyards of the era in terms of sheer scale and speed of production. If you were to go and visit one of these shipyards on any given day during this time, you'd be met with a flurry of activity and noise. Workers in their overalls, helmets, and leather gloves, heaving their equipment with them as they dashed between workstations. It was something never seen before in shipbuilding history. A purpose-built assembly line, more like a car factory, run like clockwork and capable of churning out completed ships at unprecedented rates. But what's more, the switch from riveted construction to the use of welding, along with the urgent necessity of labour to help maintain production schedules, afforded an extensive workforce of comparatively unskilled workers the opportunity to add their own contribution to the war effort. Many of us are familiar with Rosie the Riveter, but the lesser-known Winnie or Wendy the Welder soon started appearing in various recruitment campaigns. Thousands joined the burgeoning workforce, even travelling from other parts of the US to do so, drawn by the promise of better wages, the learning of new skills, and the opportunity to do their bit. A significant number of the new welders on these shipyards were women or those from minority backgrounds. Never before had there been the same working opportunities available to so many. Unlike with riveting, which required more extensive training, welding was simpler and quicker to learn, with one new female welder quoted as saying it was just like sewing. Though it wasn't without its drawbacks. Working days were long, and the work itself was physically arduous and at times very dangerous. The War Shipping Administration was an agency set up to oversee the operations of civilian yards across the US, as well as coordinating with the British merchant bodies. They put into practice the construction of a suite of new ships, each designed to fill a crucial role in the war effort and be built quickly and cheaply. Victory ships were large cargo vessels that displaced around 15,000 tons. They could be up to 455 feet, 138.7 meters in length. Impressive vessels in and of themselves, but joining them on the stocks was a dazzling array of specialist tankers and vessels, chief among which were the T2 family of tankers, long, utilitarian ships designed to ferry petrol, diesel, and black crude oil across the Atlantic to power the ships, tanks, and trucks intended to land in France. But before the Victory ships, the real jewel in the crown of the emergency shipbuilding program were the Liberty ships. Incredibly, more than 2,700 Liberty ships were built across just 18 shipyards between 1941 and 1945. And by 1944, average construction times are said to have been around 42 days per ship, compared to a previous average production rate of around 245. In one remarkable instance, the Liberty ship SS Robert E. Peary was built in a record 5 days as part of a morale-boosting propaganda effort. Now, these ships and the people creating them were making the impossible possible. Capable of carrying over 10,000 tons of cargo and over 441 feet long, the Liberty ship was adapted from existing British plans and appealed in its relative cost-effectiveness and fast construction potential. They were originally designated EC2SC1, that is, emergency cargo between 400 to 450 feet, where S referred to their 2,500 horsepower triple expansion steam engine, and C1 their specific design. These utilitarian ships were, on the whole, a little outdated. They were slow, and according to many, they weren't much to look at, even earning the nickname Ugly Ducklings. But despite this, they'd play a crucial part in delivering weapons and supplies to Allied troops, providing a key lifeline that finally offered a way to counter the devastating effects of the U-boats. President Franklin D. Roosevelt stated that these ships would bring liberty to Europe, effectively coining the name that they would come to be referred to forever. They'd become a symbol of hope, strength, and resilience. But not all was well. Liberties had been designed for mass production. Now, it might seem immediately apparent that anything that's set up to be manufactured quickly, cheaply, and with the use of relatively unskilled workers should immediately raise a question of quality and durability, but so far at least everything seemed to have been going according to plan. But this was about to change. The first truly significant blow to this new surge in shipbuilding came in the form of the SS Schenectady, and she would certainly not be the last. While fractures of varying extents had previously been reported in a number of different ships, nothing as bad as this had ever happened before. The Schenectady was actually a T2 SE A1, or a T2 tanker, effectively the tanker counterpart to Liberty ships, which was built by the Kaiser Shipbuilding Company, and the Schenectady was the first to be constructed at the new Swan Island shipyard. At around 523 feet long, though almost comically small in comparison to modern equivalents, these 6,000 horsepower tankers were both bigger and faster than the Liberties, capable of speeds around 15 knots, compared to the more sluggish 11 knots of the Liberty ship. Now, originally, these were intended to use steam turbines, but a shortage of the available machine tools necessary to make the gears meant that they would instead turn to turbo-electric propulsion. As with the Liberties, the workhorse T2 fuel tankers were a crucial asset to the war effort, delivering crude oil, petrol, and diesel to those fleets already out at sea, fuel that they were completely dependent on. As such, the Axis knew to target them. That meant that, just like the Liberty ships, speed was the name of the game when it came to the construction of these vessels, and production time for the T2 tankers was rapid, with 533 of them being built by the US from 1940 to 1945, courtesy of the United States Maritime Commission. The SS Schenectady's construction was completed ahead of schedule in December 1942, but then, not even 1 month later, without warning, she fractured almost completely in two while sitting still, moored at her fitting wharf. The water was calm, the weather was mild, there was no discernible reason why this had happened, and yet the sight of the vessel jackknifed where she stood in the fitting out berth, along with the immense noise that accompanied the split, was undeniable. Now, this was unfortunately just the start of the problem. Later that year, a Liberty ship would befall a similar dramatic fate. The 422-foot, 7,176-ton SS John P. Gaines, named for the Army officer and politician John Pollard Gaines, had been built by the Oregon Shipbuilding Company and launched on 11th July 1943. On the night of November 24, 1943, around 100 miles off the Alaskan coast, she was busy undergoing her second voyage, setting out from Dutch Harbour in the Aleutian Islands, headed for Seattle. The North Atlantic was facing an increasingly rough winter with plummeting temperatures, powerful swells, and winds up to 100 knots. It was in just such a storm that the SS John P. Gaines would meet her fate. At around 10 p.m. ship's time, the crew of the vessel reported hearing sudden, loud cracking noises, loud enough to register even over the roar of the ongoing storm. Knowing it would be impossible to identify the source of the noise in the crushing darkness, they continued on, but then, at 2:41 a.m., when all but the watchmen were asleep, disaster struck. The waves, which had already been wreaking havoc on the ship, had only intensified as the night wore on. A surge struck the vessel, then another, causing her to bend dramatically, and then, with a terrible metallic grinding, the ship's hull was torn in two, the bow drifting away and sinking below the inky water. As it turned out, the initial noises heard aboard the ship had been the beginnings of a port side fracture from the number 3 cargo hatch. The repeated forces of the waves caused the break to propagate out towards the deck and ultimately tore it apart. Luckily, due to the effective warning bell that the early noise had signalled, those on board had already moved to the relative safety of the stern. As they awaited rescue, they had to pray that what remained of the John P. Gaines wouldn't capsize. The ship's 4 lifeboats were launched, stationed nearby the stern in case it too should founder, and the crew struggled to make sure that her exposed bulkhead was turned to be protected from the relentless wind and waves. Volunteers threw together makeshift life rafts from strung-together oil drums and hastily cut wood. Incredibly, the watertight bulkhead held, managing to keep them afloat until help arrived 33 hours later. Survivors were loaded into the lifeboats, cold, wet, and tired, only lightly clothed in the icy conditions thanks to how quickly they'd had to jump from their bunks during the night. The rescue efforts went on through the small hours. Grappling with the darkness and roiling waters, they attempted to set lines between the rescue ships and the wreck, but tragically, one lifeboat carrying 10 men was swept away after the heaving line broke, and it was never seen again. The 4th and final lifeboat was picked up the next morning, and the 70 total survivors of the John P. Gaines were delivered safely to Seattle, their ordeal finally over. Something was clearly up with these emergency wartime ships. In the end, some 1,500 examples of what were deemed significant fractures, that is, cracks in the steel, were discovered in the shell plating of their hulls, and 12 emergency wartime ships had broken apart without warning before the war was over. Hundreds and hundreds had been built, and they'd served well without being lost to structural failure, but enough had been lost that alarm bells were starting to ring, and then, 7 years after the war had finished, it happened again. It was the same nor'easter that had sunk John P. Gaines that took down 2 more World War II-era T2 tankers in February 1952. Built by the Sun Shipbuilding and Dry Dock Company and launched towards the end of 1945, the 10,000-ton SS Fort Mercer never actually saw service. Though the war was now over, many wartime T2 tankers were actually still in use. Some were being sold off and turned even into passenger ships, some were allocated and redistributed to US owners, and others were acquired by the US Navy. In the 1950s, both the SS Pendleton and the SS Fort Mercer were being used for fuel transport. Another product of the Kaiser shipyards, the Pendleton, like the Schenectady, had her start at Portland's Swan Island Yard. It was Tuesday, 12th of February 1952, that she set off from Baton Rouge, Louisiana, bound for Boston, carrying 122,000 barrels of kerosene and oil. That same morning, the SS Fort Mercer departed Norco, Louisiana, with full cargo and a crew of 44 headed for Maine. The first few days at sea were without incident, but by that weekend, as both ships neared Long Island, the wind started to pick up and the waves got choppier. A storm had begun to set in, one that would become one of the worst seen by the area in living memory. The crew of both vessels were now facing a perilous battle with the elements. Sea heights reportedly reached as much as 60 feet. Visibility was minimal with the snow driving on, and 70-mile-per-hour winds were so strong you had to lean into them just to keep your feet. The gale was only worsening as the hours passed, and then, a little before 6 a.m., Monday, the 18th of February, as the Pendleton continued to be buffeted by the waves off the coast of Cape Cod, an explosive sounding cracking was heard. More quickly than anyone could possibly have the time to comprehend what was happening, the SS Pendleton ruptured in half between the number 7 and 8 cargo holds. There had been no warning signs. The bow section was rapidly carried away by the storm, along with the Pendleton's captain, John J. Fitzgerald, 7 other crew members, and the ship's radio room, leaving the remaining 33 crew members on the stern section with no way to send a distress call. They were completely alone. They acted with remarkable courage, keeping calm, and they worked quickly, shutting the watertight doors, and in doing so, enabling the stern section to actually just stay afloat. In lieu of a radio SOS, they managed to blow the ship's steam whistle by rigging it to a line and heaving on it. Now all they could do was wait for help. That is, if anyone would come at all. The Coast Guard was, however, already preoccupied. Around the same time as the Pendleton was grappling to stay afloat, the Fort Mercer was to become yet another T2 tanker to break in half. But in her case, though, the men were at least given a little more time to prepare. The first sign of what was to come arrived at 8:10, when, all too familiar by now, a whip-like crack was heard and the ship's load of oil started to spill into the surrounding ocean on the starboard side. Now, knowing full well the reputation and history of the earlier T2 tankers, Captain Frederick Paetzel turned the weakened vessel away from the waves in an effort to keep the fracture from propagating further, and then he radioed for help. At 10:30, the sound of ripping metal rang out again, and the tear near the number 5 cargo hold worsened, with still more fuel being lost to the waves. Another frantic SOS was sent out by noon. As the heavy seas continued to wreak havoc on the tanker, one last terrible cracking signaled what everyone aboard had been fearing those last few hours. The Fort Mercer's hull had been torn apart. The stern section, along with 34 of her crew, was drifting further and further away from the bow. Captain Paetzel and 8 of his men were precariously trapped in the bridge, not daring to move as the seas tossed the bow violently, and unable to do anything but watch as part of the deck was dragged below the murky waters, taking the ship's lifeboats with it. As if there wasn't already enough to concern themselves with, buffeted by the unrelenting winds, the bow, rendered completely at the mercy of the waves without any engine power, was now hurtling back towards the stern section, coming perilously close to colliding. Thankfully, the stern still had its engine, and the quick-thinking efforts of the engineers served to actually maneuver the stern out of the way of a potential collision course. 4 Coast Guard vessels, the Eastwind, the Unimac, the Yakutat, and the McCulloch, had all been diverted to the Mercer's aid. At the Chatham Coast Guard station, 2 objects had been identified by radar operators, what they supposed at first were the 2 sections of the bisected SS Fort Mercer, but a Coast Guard PBY Catalina was sent to investigate and spotted that what they'd actually identified was the SS Pendleton. And it was suddenly apparent they were dealing with not 1, but 2 ships that were split in half and in need of help, and fast. The ensuing rescue has since been immortalised in literature and film, going down in history as one of the Coast Guard's most daring rescue attempts ever to take place. It was one little motor lifeboat, the CG 36500, that managed to heed the call. At just 36 feet long, the 90 horsepower TRS model lifeboat was massively dwarfed by the Pendleton's 504-foot long hull, and surely should be no match for waves as high as 6-story buildings. The crew of 4 was led by coxswain Bernard C. Webber. To say that the CG 36500's journey to reach the Pendleton's stern was treacherous would be an understatement. Immensely powerful waves were throwing the small boat around like a cat playing with its prey, at one point causing the lifeboat to fall onto her side and both the compass and the windshield to be shattered. In the words of Bernard Webber, the other men were knocked to the deck time after time. I thought several times I'd lost my whole crew. They looked like goners, but they managed to hold on. The stranded crew of the Pendleton had been waiting all day for rescue, unsure if anyone was even aware of their predicament at all. Fireman Frank Fateau would later state that the glorious sight of the bobbing light of the approaching lifeboat left them spellbound. Upon finally reaching the tanker's towering stern section, a process which itself had taken hours, the Coast Guard's troubles were far from over. All 8 crew who'd been stranded on the Pendleton's bow were lost. There was now a desperate rush to evacuate the remaining survivors from the stern, while trying to prevent the lifeboat itself from being smashed into the Pendleton by the immense rolling waves. A light rope Jacob's ladder was lowered, and one by one the men began to make the hazardous climb down to rescue. Though the CG 36500 was only intended to carry a maximum of 12 passengers, due to the great bravery and determination of those involved, all but one of the 33 men was successfully piled into the tiny boat and brought to safety. The ship's cook, George "Tiny" Myers, who'd valiantly helped his fellow crewmen during the rescue, had been tragically lost to the sea. Meanwhile, back aboard the fractured remains of the Mercer, the 9 crewmen, including the ship's captain, had been crowded in the chart room without heat or light for hours now, and as midnight approached, the already listing bow had begun sinking lower into the sea. The men would have to move. Utilizing an improvised rope comprised of signal flags, they managed to successfully reach the forecastle ahead of them. Poor visibility and gale force conditions made their first attempts at rescue tragically unsuccessful, with 5 crewmen being lost in the process. The Coast Guard had no choice but to wait till dawn. As soon as there was enough daylight, the US CGC cutter Yakutat launched a monomoy surf boat to pick up the remaining survivors, including Captain Paetzel from the bow. Not without considerable difficulty though, using a combination of surf boats, shot lines, and a rubber life raft, all 4 men were eventually retrieved. Just 21 minutes after the last survivor had left the bow section, at around 10:51 AM on February 19th, it capsized completely. There was no loss of life from the Fort Mercer's stern section. In fact, 13 of the 34 men there opted not to be rescued straight away, choosing instead to stay on in the hope that they'd be able to possibly salvage the hulk. The stern was actually successfully towed a few days later, and eventually refitted with a new bow to become the SS San Jacinto. But the curse of the T2 tanker had not fully lifted. Thanks to an explosion in her cargo tanks, the San Jacinto would actually split in half again in 1964. So what had gone wrong? How was it that these innovative new shipbuilding techniques could result in vessels that would seem to do just fine on the water one day and then the next could suddenly break apart, even in seemingly benign conditions? The common denominator seemed to have been the new, prefabricated, all-welded ship designs. Similarities between these failures were starting to be recognised, kind of like patterns. Where significant structural ruptures had occurred, they tended to begin amidships, often when they'd been exposed to cold water temperatures, and the fractures would typically propagate out from a common origin, the square corners of the hatches. The sharp angles here created a stress concentration in the steel, exacerbated further by the frequent overloading during wartime conditions. But unlike when hull construction consisted of separate steel plates being riveted together, where each join could act as a crack arrestor, essentially preventing any fractures from spreading too far, the all-welded ships provided a continuous steel surface across which cracks could spread unimpeded. But early investigations were quick to place the blame on the inexperienced welders behind the construction of the Liberty ships and the T2 tankers. It was floated that poor quality welding had led to repeated incidents of ships breaking in two, and after all, it seemed the most obvious explanation. These weren't isolated incidents, and the evidence at the time did seem to point towards defective welding. The American Bureau of Shipping's investigations into the Schenectady's breaking up, for example, concluded that it must have been the result of locked-in stresses attributed to the apparently faulty welding. Therefore, if quality control of welding were to be improved, no further disasters should be seen. But as we know, after the Second World War, more problems did occur. Now later, as investigations reopened, it was supposed that notches in the steel rendered these tankers unable to withstand the bending of normal wave action without creating fractures. So it was proposed that the fitting of riveted steel straps across the hull could help remedy the problem. But both the Pendleton and the Fort Mercer had both been fitted with the mandated crack arrestors, so clearly significant structural failure was still going on. It wasn't until years after that those first ship's fractures had been spotted that research revealed the mystery of why these ships were splitting was far more complicated than first realized. Regardless of the quality of the welding work, these early ships could be more or less destined to fail for a much broader reason. This was in fact more of a question of metallurgy. Sure, a faulty weld certainly wouldn't help, but it was actually the chemistry of the steel used in the skeleton of the ship itself that was sealing their fates. The steel used in the construction of these ships did comply with the established specifications for standards at the time, but testing of steel like this was only required to be performed at room temperature, and only with a very small specimen size. The war industries were pushing production to a scale and speed never before seen, but this was still relatively early in the days of understanding the molecular structure of metal. Established testing methods were not yet capable of reflecting the extremes of operation. Because of this, early war mass-produced ships were effectively only being tested once they were already in use, which was of course far too late. they'd come to find that the ability to predict the performance of large steel structures would be vitally important, not just to help prevent further losses, but to help inform designers of ships into the future. Now, no testing variation was observed in riveted versus welded structures either, meaning that these tests weren't sufficient to flag the issues that would arise due to varied temperatures. But as it turned out, temperature played a huge part. Though it wasn't understood at the time, the suddenness of the SS Schenectady's breaking apart, though shocking, is a characteristic of what is called brittle failure. It was a woman named Constance Tipper of Cambridge University who first proposed the idea that it could be the properties of the ship's steel itself, not the welding work, that was causing Liberty ships and T2 tankers to become brittle. She linked the cold temperatures that the ships were being exposed to during service with a transition in steel behavior from ductile, that is relatively soft and malleable, to brittle, that is likely to shatter like glass. With variations in the steel composition and the microstructure making fracture more likely in many incidences than in others, in the case of the SS Schenectady, it was found that despite the appearance of calm weather conditions at the time her hull broke, it was more so the cold temperatures of the North Atlantic that were the problem. Because of this, she developed a way of measuring brittleness using the so-called Tipper test, which is a method that's still used to this day. Now, using the Tipper test, it's possible to predict how different samples of steel would behave at different temperatures. It was indicated that when the steel contained too high a percentage of sulfur or phosphorus, it was much more likely to become brittle and prone to breakage. These kinds of impurities in steel could result from the hastened construction process, and of course, during the war, when materials were simultaneously in high demand and short supply, it was difficult to be picky. People have often wondered why Titanic, for example, broke apart when she sank, when other liners like Britannic and Lusitania were exposed to similar stresses on their hulls during sinkings without issue. But Titanic sank in water that was freezing, and her steel contained high concentrations of sulfur and phosphorus, thanks to the relatively primitive method of casting in acid-lined open hearth furnaces back then. Titanic wasn't badly built or designed. You couldn't blame her riveters for the breakup, but she was a product of her time, and the full microscopic characteristics of metal were not yet fully understood. As far as the Liberty and the T2 ships were concerned, the proposed solution of adding riveted crack arresters was very much like putting a band-aid on an open wound. Like with updated ship designs using rounded hatch corners wherever possible to reduce stress concentrations, these measures could, and did, help prevent fractures from escalating into total structural failure. But they didn't address the actual underlying problem, in that it was the metal itself that was failing. As a result of the research into these ships that split in half, it was now clearly apparent that using inferior grade steel was not an option, something that may have gone unnoticed if not for the phenomenon of the Liberty ship's rapid construction. In spite of their clearly less than ideal start, the truth was that Liberty ships and T2 tankers and the Victory ships were all instrumental to the war effort. Simply put, the war would likely not have been won that quickly without their contribution. Although the hasty construction times had their drawbacks in terms of structural integrity, the record-breaking construction was undoubtedly a significant achievement, and still to this day, being the most ships ever produced using a single design. It's unlikely that these construction times will ever be equaled again, nor hopefully will there ever be another need for such urgency that would require so many to be built so quickly. But probably most importantly, the learnings from these early failures of those vessels helped provide the very foundations of our understanding of modern fracture mechanics, informing and shaping future shipbuilding principles and safety guidelines, learnings that were applicable to other feats of engineering too, like bridges and aircraft. In spite of all their hardships, these ships ultimately provided a win, not just for the war effort, but for the advancement of scientific research, even decades later, to this day. On the topic of judging past construction techniques from the modern day, a conclusion found by a metallurgical study on steel samples taken from Titanic's wreck summed it up very well. The steel, they said, used in constructing the RMS Titanic was probably the best plain carbon ship plate available in the period of 1909 to 1911, but it would not be acceptable at the present time for any construction purposes, and particularly not for ship construction. If the Titanic had not collided with the iceberg, it could have had a career of more than 20 years, as the Olympic had. It was built of similar steel in the same shipyard and from the same design. The only difference was a big iceberg. The same is absolutely true of the emergency wartime ships. They were a crucial asset and a product of their time, And as our understanding of science and physics has improved, so too have our own standards. Part of our great understanding today has got to be attributed to the lessons learned from the ships that broke in half. Submarines are strange in that, unlike other naval vessels, they're actually designed to sink and then rise again. It just so happens that occasionally that second part of the equation is a little bit difficult to pull off. In the pantheon of naval designs, there have been some magnificent, seaworthy warships, but brilliant design doesn't just come from nowhere. Often designers learn from their mistakes and their misjudgments from along the way. Now, we've already looked at some poor warship designs in brief on this channel before, but some designs are so poorly executed, they deserve their own spotlight. The British K-class submarine was intended to fill a gap in the Royal Navy's fleet, fast enough to keep up with the massive battleships in fleet engagements. It resulted in a bizarre design that, despite being one of the largest submarines built for the age, was also one of the most cramped and, critically, the most dangerous to its crew. Amid trials and disasters, lost boats and narrow escapes, the concept was finally scrapped, but not before dozens of Royal Navy crewmen had lost their lives. Ladies and gentlemen, I'm your friend Mike Brady from Oceanliner Designs, and this is the story of Britain's bizarre and exceptionally dangerous steam-powered submarine, the dreadful K-class boat. Our story begins just before the outbreak of the First World War in the early 1910s, where, in Britain's Admiralty, some interesting things were happening. See, back then, there had been a massive technological surge with new designs and technologies being introduced all the time. It was difficult for regulation and conventional guidance to keep up. For centuries, the most advanced warships at sea had been sail-powered and oak-hulled line-of-battle ships like HMS Victory, but the Industrial Revolution and the introduction of iron and then steel-hulled ships powered by steam engines changed everything. Then came torpedo boats as steam engine technology improved, the slower, clunkier expansion engines being largely supplanted by immensely powerful steam turbines, which could drive ships up to previously unthought of speeds. Within just a short few decades, Britain's warships had changed from awkward, half-sailing ships to fully fledged, steel-hulled battleships like HMS Dreadnought, fielding monstrous guns and capable of cracking top speeds. Now, that wasn't all. The submarine had been a figment of science fiction not long before, but by the late 19th and early 20th century, it was a fully realised bit of military tech. Battery and then diesel engine technology improved more and more. It meant that subs could go along on the surface with their diesel engines thumping ahead, while below they could use their electric motors, which were quieter and crucially wouldn't create any kind of dangerous fumes. Now, this age of technological leapfrog, the stage was set for a showdown of international and epic proportions because, of course, Britain wasn't just the only nation doing it. America, France, Italy, and especially Germany began to pump funds into their navies as well in the battle for international glory. And for Britain, Germany was the biggest concern. The closest thing in more recent years would be probably the USA and USSR's space race, a lasting and bitter rivalry like that. Britain's military planners began to envisage a showdown with Germany in one or more massive battles at sea. The only problem was these new style of warships had never really been proved before in battle. It was a whole different game, so the hypothetical reigned supreme. And this is the kind of fluid, fast-tracked environment that encouraged a few of the more creative ones among the British Admiralty to propose designs that, on paper at least, sounded interesting. And in 1913, thought was put towards a new class of submarine whose purpose and function was entirely original, but which would prove disastrous. Because submarines were such a new piece of technology, nobody really knew what purpose they could ultimately serve in the outbreak of war. They had some serious drawbacks, which limited, at least in planners' eyes, their usefulness, and truth be told, they were seen more, before the First World War, as a bit of a curiosity, even a toy. Surface warships had ruled the waves for centuries, and the advocates for submarine warfare, who were real visionaries of their time, were scoffed at by colleagues and higher-ups who saw them as boffins playing with their toy boats. For one, surface warships like battleships were really, really fast, much faster than submarines. Subs used their diesel engines, but in the pre-war world, the diesel engine itself was in its infancy. Early diesel engines were quite underpowered. The reason that diesels actually had to be used in the first place were twofold. First, diesels burn their own fuel oil, which is injected right into the engine and doesn't need massive boilers like steam engines do. This means the inside of the submarine, already cramped because of the necessary pressure-bearing form of the hull, isn't taken up by a massive steam power plant, especially those boilers. They just wouldn't really fit. Secondly, coal and steam are dirty and, in confined spaces like a submarine, extremely hazardous. In big ships of the age like Titanic, massive ventilators were placed all along the upper decks to get as much fresh air below as possible. Without it, the boiler rooms would become uninhabitable and the stokers and engineers would suffocate in 70-degree air and choke in coal dust. How would that arrangement work in a submarine, which is a confined space where holes for ventilation cannot really exist without seriously hampering the sub's ability to dive? This is, by the way, what we in the industry call foreshadowing. The short of it is that submarines were slow on the surface, able to achieve just about 15 knots at most. Now, that isn't that sluggish, given that at the time, most big merchant ships chugged along at about 12 knots. It meant that well-positioned submarines could engage enemy shipping by cutting them off on the surface before diving to attack. Below the surface, the submarine's electric motors pushed the subs along at speeds that were much slower, about 9 knots. Not fast enough to catch up to any real enemy ship unless they were crippled in the water already. Now, for many Navy planners, that only reinforced the idea in their minds that the submarine was little more than a toy, that it would be useless in engaging the Kaiser's battleships and battle cruisers, which, by the way, could steam at least 10 knots faster than a British sub on the surface, and that was that. But then, there came some alarming news from Europe. In 1913, someone, somewhere, had leaked intelligence that said Germany was preparing a new class of submarines that would overcome all of these issues, that the new German boats would be able to keep up to the pace and steam over 20 knots. They could maintain pace with battleships and destroyers. Now this changed the game because it meant that the new German submarines, if introduced, could sail alongside larger fleets of battleships and cruisers, keeping up the pace until the enemy fleet was spotted, and then they could dive and hunt freely from below the surface at the vanguard of the action and sink capital warships left and right, cutting off retreat and routes of escape. It was a terrifying thought. It's just a shame for the British Admiralty that these reports were incorrect. Now, even if the German boats didn't actually exist, it really seemed a possibility at the time. Germany's submarines were well developed because, unlike the British Admiralty, German naval planners took them a little more seriously, and the diesel engine had been refined by German manufacturers to a higher standard than Britain's. The response was swift, frantic even. Britain needed its own fast submarines. The challenge had been issued, and a design specification was put forward. At the time, the most advanced British submarine was the E-class boat. It was about 180 feet, or 55 metres long, and of around 660 gross tons displacement on the surface. The cylindrical pressure hull could fit 30 crewmen in cramped but relatively cosy conditions. They were powered by two 800 horsepower Vickers diesel engines above the water, and those boats could dive and then switch over to a pair of electric motors which are outputting around 600 to 840 horsepower. It meant the E-boats had a top speed of 15 knots at the surface and about 9 or 10 knots below. Now, obviously, this kind of speed just wouldn't contend with those fast German boats. Speeds in excess of 24 knots had been reported. Way more speed would need to be squeezed out of these submarines if Britain was ever going to keep up. The boats would need to be big. Larger vessels move faster through the water, for one thing, but they would need to be big to provide a stable platform for the immense engines that would be needed to actually hit those ridiculous speeds. They would need to be at least double the length of the E-class and more than double the displacement at about 1,500 tons. But there, details began to get murky because obviously the speed would need to come from the engines, but which engines? Diesels were thought to be too primitive to be able to hit the required power, but steam engines provided a whole fresh selection of issues already evident to many in the Admiralty. In fact, future First Lord of the Admiralty, Sir Jackie Fisher, apparently famously remarked that the most fatal error imaginable would be to put steam engines in submarines. But then, the design's development was actually halted because an opportunity to test the idea came up. A different proposal had been made for a submarine capable of international and long-ranging service, capable of speeds of around 20 knots on the surface. So, for this design, two prototypes would be built to test the two different options. HMS Nautilus with the more powerful diesels in a showdown against HMS Swordfish and her turbine steam engines. The proposed high-speed submarine's future would depend on this test. And the only reason steam turbines had become a viable option in the first place by that point was because they could, by 1913, burn fuel oil instead of coal, which vastly reduced the amount of dust and misery that the crew would need to endure. Vickers Shipbuilding at Barrow-in-Furness, England had basically held the monopoly on building submarines and their diesels for the Royal Navy. They would build the diesel-powered Nautilus, but in a stroke of healthy competition, encouraged by the head of submarine service, Commodore Roger Keyes, the second design, powered by steam turbines, HMS Swordfish, would be built in Scotland. They would both need to be quite big, well over 200 feet, around 1,000 to 1,400 tons. Now, work had got underway in 1912, and the proponents of the fast fleet submarine design would be watching closely. Already there were doubts that the diesel engines could do the job, and we already know that there were reservations about using steam engines. In the end, the test would never be conducted as intended because the war rudely interrupted proceedings in 1914, as Nautilus was sitting at the fitting out wharf and Swordfish was still under construction on the slipway. Now, what happened next shocked a lot of the Admiralty's submarine naysayers. Suddenly, German U-boats began to do devastating work on British ships. The submarine SMU-9 pulled off a major coup in September 1914 when she caught 3 old British cruisers as they were sailing, unprotected, on patrol. She sank one after another and killed around 1,500 men. SMU-35 alone would go on to sink 220 Allied merchant ships during the war for a total tonnage of over 500,000 tons. Now suddenly, the submarine didn't seem like much of a toy anymore, and the Admiralty took their own subs very seriously indeed. German U-boats were quite quick on the surface with their powerful, advanced diesel engines able to achieve close to 17 knots. They were bigger too than their British rivals, and improved design was needed and fast. Quickly, the old pre-war plans for the fast submarine designs were dusted off and, without being able to properly run HMS Nautilus and HMS Swordfish up against one another since they were still under construction, Vickers provided a design for a boat they hoped would be able to hit those long-desired fast speeds. Vickers simply designed a bigger submarine than they'd used before and fitted their biggest diesels possible. Massive 12-cylinder units capable of outputting 1,200 horsepower each. Now, the new class of sub would get no fewer than 3 of these, each driving its own propeller. The resulting boat was called the J-class submarine, and although it was a fine boat, it fell short of the speed requirement. They were still impressively fast on the surface, but they maxed out at about 19 knots. Faster than the German submarines, but nowhere near as fast as the other battleships or surface units. For the British, it should have been the writing on the wall, the sign that technology just wasn't there yet, but instead, the Admiralty began to seek out other options, and there, powering their fast battleships, were the fast steam-powered turbines. And what if they could be fitted to a submarine? Eyes turned towards HMS Swordfish, which, in April 1916, had been renamed HMS S1. The boat had a pair of geared steam turbines fed with steam from oil-burning boilers. The submarine was big, but the massive, heavy machinery made her sluggish to turn and dangerously unstable. She could only hit 18 knots on the surface. But still, what if the turbines were yet more powerful? What if the boat were larger? Surely that would work. Well, the Admiralty must have thought, in their wartime desperation, that it was a worthy endeavour. The K-class submarine was born, a class soon to be known as the Calamity class, and for good reason. The primary issue with the K-class boats was the choice of propulsion. Steam turbines are very big and very heavy. They need accompanying boilers which themselves are also very big and very heavy. The fumes from burning the oil need to be adequately vented through funnels. The boilers themselves raise temperatures in the surroundings to alarming degrees. Now, these all presented design challenges that the Admiralty had to overcome. They started by making the K-class into a monster of a submarine. The old E-class boats had been about 180 feet or 55 meters long, but the K-class boats would be a whopping 339 feet or 103 meters in length. Now, looking at the plans, it's clear to see why. An enormous amount of the submarine's interior would need to be taken up by the massive propulsion, the boilers, the turbines, and the auxiliary machinery. In fact, about half the sub's massive length is taken up by the machinery alone, giving the K-class crews the unique and unfortunate distinction of serving in both the largest and the most cramped boats in the fleet. Now, the idea was for the K-class to use their turbines to steam along at 25 knots on the surface, but then dive below and switch over to their electric motors as usual. To charge the batteries and provide a backup power plant, a diesel generator was fitted for good measure, which took up yet more space and added more weight. Now, driving along at 25 knots sounds well and good, but in the event of a crash dive, the crew of a steam-powered submarine are presented with a unique situation. To vent all the gases and smoke out of the boilers, funnels needed to be fitted, which meant, to put it simply, so did holes. Too many holes. Submarines rely on their watertight design and the elimination of natural weak points in their hulls in order to stand up to the crushing pressures at depth. Adding more holes into a submarine's hull is just about the worst thing designers could do. It just added more possible failure points. The crews would need to be impeccably well drilled and trained to close all the vent hatches and trunking off to the water in order to actually dive the boat. Now, in practice, this proved to be a fairly elaborate procedure and added just more steps for the sub's crews to keep track of under pressure. This too, by the way, is a nice bit of foreshadowing. The first K-class boats were completed by May 1916, and the good news was that the ever-reliable and powerful steam turbines could do their thing, and the boats could zip along at about 24 knots on the surface. Unfortunately, that's about where the good news ended for these white elephants of the sea. The boat's massive length and bulk made them extremely difficult to control, as Swordfish had been in testing, but the issues of controllability were almost nothing compared to the issues with the process of actually diving. The idea went like this. If running on the surface at speed under steam power, then the boilers' furnaces would first need to be safely doused and put out, because if they stayed burning below the surface, it could prove lethal to the crew thanks to the buildup of gases and fumes. Hydraulics would lower the smokestacks into wells in the deck and secure them in place, while the holes left behind for venting the smoke would be closed over with hatches. The other holes that were needed to feed the boilers with air from above and seawater from below, called the main injectors, would all need to be closed and secured as well. Only then could the submarine attempt to dive. But here too was an issue. The hole-filled hull meant the K-class sub could have a maximum safe dive depth of about 200 feet or 61 meters. Now, this was similar to the older E-class boats, but the K boats were more than 200 feet long, and it meant that the submarines, which are already hard to control, could dive improperly trimmed, with one end of the ship still on the surface in plain view, and the other end approaching maximum safety depth. Crews were said to sardonically quip, "I say, number one, my end is diving. What's your end up to?" Speaking of the crew, it seems almost as if there was something of an afterthought when it came to designing the K-class boat. How exactly 60 men were supposed to live comfortably in close-packed conditions with boilers running hundreds of degrees behind them is unknown. Of course, conditions were hellish, with temperatures nearly unbearable, and humidity was absolutely off the charts. The massive exterior size of the K-boats was offset by the fact that around half their length was packed full of machinery. Men sweated and suffered down below as their boats lumbered and stumbled over the waves. Testing got underway, and the results, aside from the speed, were worrying. First of all, the elaborate dive process was difficult to pull off quickly. The quickest K-boat dive speed is argued about to this day, with times ranging from 5 to about 30 minutes. Now, the original design specification called for a dive time below 5 minutes. In practice, a safe dive took somewhere around 20 to 25 minutes to pull off, but a crash dive could be effected by ignoring, or at least rushing, certain safety protocols in close to 4 minutes or so. But in a sub full of hatches, vents, holes, and burning hot boilers, rushing it is something the crew would probably not want to be doing. Surface testing showed the subs capable of their design speed, but nearly impossible to turn effectively. It was said that they had the speed of a destroyer and the turning circle of a battle cruiser. Now, that wasn't all. The boats had low freeboard. There just wasn't enough of them above the waterline, considering their enormous weight and bulk. They would ship massive amounts of water over their bows as they steamed at speed, but fortunately the crew were given a fully enclosed bridge on the deck to make up for it. Now, all these issues and failures of logic were to catch up with the K-class boat and the submersible destroyer idea itself. First was K-13. She was on her sea trials in January 1917, which culminated in a series of dives. The boilers were doused, the vents were shut, and the funnels folded flat, and down she went. But she did not come up. A vent hatch had failed to close and lock, and at depth, water roared into the turbine engine room. 80 men were on board, including her crew and members of the shipyard that had built her. The submarine sank, and despite blown ballast tanks, it went down to the bottom. Messages were sent up from below in capsules, and remarkably, K-13's captain was able to escape. He reached the surface and began to coordinate a rescue mission. But inside the sub, the engineers had calculated there had been just about 8 hours of air left, and the saga of getting the boat's skipper up had chewed up about 7. An airline was attached from rescue vessels above but couldn't pump any down. From below came Morse code tapped on the side of the hull by the survivors inside. Give us air, over and over. And finally, the blockage in the line was identified, it was successfully passed down, and the sub's bows were refloated to the surface enough that holes could be cut in and men could get out. Just over 30 had died, mostly trapped and drowned in the massive engine rooms aft. Reports showed that the main vent hatch in the engine room hadn't shut, and in fact, indicators in the command room had showed that it was open. But when one factors in the human element, it becomes clear that so complicated a dive process as the K-boats had introduced many different points of failure. The Admiralty had other ideas. The first 6 K-boats were put into their own flotilla and given the bizarre task of hunting the smaller, nimbler German U-boats. Now, the K-boats' issues are legendary, and their spotted careers border on the monstrously unlucky and the unjust. K5 was conducting trials when she went for a routine dive, but was never heard from again. K3 dove out of control to way below the safe 200-foot dive depth, hitting a maximum of 266 feet, somehow avoiding catastrophic crush failure. The boat managed to surface and she actually survived. HMS K12 took her sea trials in the same lock as K13. She encountered a similar issue and ended up stranded on the bottom, but fortunately her crew were rescued. Then, the same thing happened to K16. Morale in the submarine flotilla plummeted during the First World War. As if conditions weren't already bad enough, word had got around that a new bulbous bow was to be installed on the remaining K-class boats, indicating to the crews that the Admiralty thought them incapable of adequate seakeeping. The problems of containing hot steam and boilers within a submarine hull were tragically demonstrated when K-26's steam lines failed and scalded 2 stokers to death with superheated steam. Men who volunteered for service in submarines and were assigned to the K-class boats began to refer to themselves as the Suicide Club. The K-class boats' ungainly bulk earned them a reputation for terrible, terrible handling as crews of other vessels watched them bumble about. And in late 1917, the flotilla was out, at last, steaming alongside large fleet ships as they had been designed to do. When the cruiser HMS Blonde set a new course, it caused chaos. The K-boats altered their courses too, but their awful maneuverability in the close confines caused a fender bender, and K4 slammed straight into K1. In January 1918, though, the K-boats suffered their most infamous incident. The entire Grand Fleet was to undertake exercises off the Orkney Islands. The K-boats had been split into 2 flotillas, the 12th and ominously the 13th, and they set off, each led by a lead vessel. For the 12th, the cruiser HMS Fearless, and for the 13th, the destroyer HMS Ethereal. Passing the Isle of May at the mouth of the Firth, things began to go horribly wrong. Lights were spotted by the 13th flotilla ahead, and the vessels changed course to avoid them. They were probably fishing trawlers or other small merchant vessels, but in typical K-boat fashion, K14's rudder jammed, and she swerved off into the night and out of line. K22 behind her had lost sight of her flotilla mate, when to their horror, the submarine was spotted dead ahead across their bows. Now K22 cut straight into K14, and they stuck fast. The massive battlecruisers from the fleet swept past, and one gave K22 a good tap as she went by, causing serious damage and more flooding. Now the submarines were floating dead still in the water, incapable of moving and not sinking, thanks to their watertight doors. The 13th flotilla received word of the collision and turned back to help their comrades. HMS Ethereal and the other K-boats fully illuminated to prevent a collision from turning and running back through the main fleet while heading back to K22 and K14. But suddenly, out of the mist appeared the 12th flotilla, with HMS Fearless at the lead, and the result was catastrophic. Fearless smashed through K17 and cut her nearly in half and left her sinking, while K6 smashed into K4, and the two were locked together and began to sink. Now, all the other boats twisted and turned to try avoiding one another, creating a scene of absolute utter confusion. Dozens and dozens of men were left in the water, and then the unthinkable happened. The 5th Battle Squadron, 3 dreadnoughts and their escorting destroyers came barging through at near full speed. The men in the water were run down and killed by the score. Nobody from K4 survived, and 48 from K17 died as well. In the end, around 105 men lost their lives, 3 K-boats were badly damaged, and 2 were sunk outright without ever having encountered the enemy. But the tragedy came to be sardonically referred to as the Battle of May Island. Now, it should have been the end for the K-class as a concept, but remarkably they were kept on until well after the war had ended. In May 1918, K-15 took a huge sea in through her funnels, which extinguished the boiler furnaces, leaving her powerless and with a flooding engine room. The stern sank, but the bow was left with just enough buoyancy to float above the waterline, thanks to her fast-acting crew. The ballast tanks had their valves jammed, and it took 8 harrowing hours for the boat to be properly refloated. Now, this speaks nothing of the many collisions and near accidents throughout the boat's careers. It seems like even despite the design issues and faults, the boats were just haunted by some kind of curse. K7 had finally got a clean shot at an enemy submarine on the surface. A spread of torpedoes saw one hit the German boat fair and square on the conning tower, but it failed to detonate. Despite the class's many failings, it has to be pointed out that the men that actually crewed and operated them worked like lions to make the submarines work at all, and they're deserving of every praise. In the end, the concept of a fast, fleet-action submarine fielding steam turbines was soundly and decisively disproven. Ironically today, modern nuclear submarines are equipped with reactors that are essentially a refinement of steam propulsion in a way, but unlike those hungry boiler-powered K-class boats, they don't need the huge amounts of ventilation and extraction, and they certainly don't need any funnels. Between 1921 and 1926, the K-boats were scrapped, with a couple of incomplete hulls used to create a new diesel-powered boat called the M-class. In the 1920s, a fleet submarine capable of quick speeds was designed and could hit 22 knots thanks to advances in diesel engine propulsion. The story of the K-class submarine is like that of Icarus, the Admiralty aiming for new and exceptional technological heights, only for them to be reminded of the lethal consequences of overreaching. After all that, it's still difficult somehow to look back on planners and designers from back then with too much of a judgmental eye, considering that so much of this technology had been untested and it was in its infancy at the time. But even so, Lord Jackie Fisher had known it way back in 1913 when he had said that the most fatal error imaginable would be to put steam engines in a submarine, and he was proven tragically correct.